Hello, we're looking at basic derivative rules today, as well as position and velocity. So I just want to go over position and velocity again and explain in a little bit more detail what's going on. So position is going to be a measure of distance. And when we're talking about distance, we're thinking of units like meters, inches, feet, those types of units. All right? And then velocity is our change in position. And the way we talk about change in position is the derivative of position. So this is going to be the first derivative. And the reason that is because, once again, velocity is the change in position relative to a change in time. So for velocity, we're going to have our velocity, v of t, is equal to the derivative of our position, s of t. All right, so s of t is going to denote position, and v of t is going to denote velocity. Units for those would be like meters per second, inches per second, feet per minute, anything that's a measure of distance over a measure of time. Right? So that's just a quick explanation of why velocity is the derivative of position and talking about some of the units we'd be looking at there. So now that we've talked about that, let's dig into this problem about a silver dollar. So a silver dollar is dropped from the top of a building that is 1,362 feet tall. So when we drop something, our initial velocity, since we're just letting go of the object, is going to be 0. So if we're looking at our position function equation, we have negative half of our gravity acceleration times t squared. Just write it like this, plus our initial velocity times t, plus our initial position. So since we're talking about feet here, we're using 32 for our gravity. If it were meters, we'd use 9.8. 0 for our initial velocity. Our position is 1362, so that's going to be my initial position. So my position function is going to be negative 16t squared plus 1,362. So that's our position function. Our velocity function is going to be the derivative of our position function. So for this, we're using two derivative rules. We're looking at the derivative, the power rule, which says we take down the exponent and we make the exponent one smaller. And we're looking at the constant, which says the derivative of a constant is 0. So my exponent is 2, so I've got 2 times negative 16, t to the 2 minus 1, and I've got plus the derivative of a constant is 0. 2 times negative 16 is negative 32, t. So that's our velocity equation. So this is our answer, this is our answer to A, the position and the velocity equation. Now we're looking at average velocity, which, remember, velocity is going to be our change in position over our change in time. So average velocity on the interval 2 to 1 is going to be our position at 2 minus our position at 1 over 2 minus 1. Because remember, an average rate of change is our slope. So I'm going to have negative 16 times 2 squared plus 1,362 minus negative 16 times 1 squared plus 1,362. And then I've got 2 minus 1. And when you do that, you're going to get negative 48. So our velocity, average velocity, so the unit for that This problem is going to be feet per second. All right, and then we're looking at our instantaneous velocities. So that means we're using our derivative of position equation that we found in A. So I've got negative 32 times 1 for my instantaneous at 1, and for my instantaneous at 2, I've got negative 32 times 2. So negative 32 feet per second. And negative 64 feet per second, respectively. All right, and then we're looking at part D. I'm just going to give myself some space here, temporarily get rid of these problems. We're looking for the time we hit the ground. So that's going to mean our position is going to be 0. So we just have to solve this equation for t. That division, you're going to get 85.125, and then you do the square root, and you get t equals 9.23 seconds. Then we're looking for the velocity at that time of impact, so this was d. So if the impact happens at 9.23 seconds, we're going to do the velocity at 9.23. Negative 32 times 9.23. And when you do that, you're going to get negative 295.24 feet per second. It's going pretty fast by the end there. So I'm going to clear this out, and then we can look at the remaining problems. Using 4 rules for all of the problems that follow. We're going to be using the power rule, which says we take that exponent down out front and we make it 1 smaller when we do the derivative. We're going to be using the constant rule, which just means the derivative is 0. We're going to be using the derivative of cosine, which is negative sine. We're going to be using the derivative of sine, which is positive cosine. So I'll just put that there as kind of a reference for us as we go along. Our first one, we've got negative 3/2 x to the 4th. So we take down that 4. We've got 4 times negative 3/2 x to the 4 minus 1 minus, and then my exponent for this next one is 2. So I take that down times the original coefficient, and then I've got plus 1 times 11 x to the 1 minus 1. So 4 times negative 3/2 is negative 6, x to the 4 minus 1 is 3. Then over here we've got 2 and 14 reduces to 7, so negative 3/7 x, and then 1 times 11 is 11, x to the 0 is 1, so 11. All right, once you know that the derivative of anything with just x to the first is the coefficient, you don't have to write that step out anymore. So that's our first one. Let me move this out of the way for us. If I can grab it. All right. So for this guy, pull down your exponent. You've got 2 times 3/8 x to the 2 minus 1 minus 1 times 9/2 x to the 1 minus 1 plus the derivative of a constant is 0. So 2 and 8 reduces to 3/4 x to the first minus 9/2 because x to the 0 is 1. Then we're looking over here. We've pulled down our exponent. So we've got 4 times negative 13 over 16 minus 2 times 1 x to the 2 minus 1. Derivative of the constant 11 is just 0. So 4 and 16 is going to reduce to 4, so we've got negative 13 fourths. Whoops. X to the fourth. X to the third minus 2x as our derivative. Over here we're looking at cosine and sine. So derivative of cosine is negative sine, and derivative of sine is cosine. So that's going to change my negative 11, right, to negative sine. So I got positive 11 sine x minus 7 cosine x. Winding down here, we've just got a couple more to look at. We always have to rewrite our expressions as exponents, like fractional exponents, or with the variable in the numerator. So here this would be 6x to the 1/2. Once we have that, we're ready to use our power rule. So take down your exponent, you've got 1/2 times 6, x to the 1/2 minus 1, or 3x to the negative 1/2, which is the same as 3 square root x on the denominator. Same thing here, bring your x up top using a negative exponent, then you're ready for your derivative. So we've got negative 2/5 x to the negative third, or negative 2 over 5x cubed. These ones are already fractional exponents, so we can just go ahead and do our derivative. Pull down your exponent, make it one smaller. So you're going to have 8x to the negative 1/5 minus 5/2 x to the negative 3/4, which we can rewrite using those negatives to put it on the denominator, and our radical rules to make it 5th root x to the first minus 5 over 2 4th root of x cubed. All right, last one, rewrite it on the numerator or up top with a negative exponent. Do your derivative. You've got negative 7 times 3, x to the negative 7 minus 1, or negative 21, x to the negative 8, or negative 21 over x to the 8th. All right, go ahead and try the I do sections, which starts with this next problem.